All right, folks, buckle up for this one because we're diving into some pretty dense physics today. We're talking Z's prime bosons.
Yeah, those.
Yeah, it sounds intimidating, I know. But that's what we're here for, right? To break it down and see what's so fascinating about these hypothetical particles.
Exactly. It's a real detective story in the world of particle physics.
Stacks of research on this one, all thanks to your requests.
Glad to be here.
So let's start with the basics. What exactly is a Z's prime boson? Like, if you had to explain it to your grandma, what would you say?
That's a good one. Okay, so you know how magnets attract or repel each other?
Sure.
Well, in the quantum world, forces are carried by particles, like little messengers.
Okay, I'm following.
And one of these messengers is the Z boson, which is responsible for something called the weak force.
The weak force. That sounds kind of wimpy.
Don't let the name fool you. It's actually responsible for some pretty important stuff, like radioactive decay.
Oh, right. So that's how atoms transform.
Exactly. Now, a Z's prime boson would be like a heavier, undiscovered cousin of the Z boson, potentially carrying a whole new force that we haven't even detected yet.
Whoa, okay, so like a new fundamental force of nature.
That's the idea. And one of the ways we think these Z's prime bosons might interact with other particles is through something called couplings.
Couplings, like what they're holding hands with other particles.
Not quite, but I like the image. Imagine it more like a language that particles use to communicate.
So the Z's prime boson might be speaking a whole new dialect.
Exactly. And the strength of those couplings, like how fluently it speaks this language, would depend on which specific theory it comes from.
Ah, okay, so finding the Z's prime boson is also about figuring out the right language to describe new physics.
You got it. For example, some theories predict a Z's prime boson that prefers to chat with leptons, which are particles like electrons and muons.
Leptons?
Yeah, they're like the lightweight particles in the standard model.
Okay, so if a Z's prime boson is hanging out with leptons, what would that tell us?
Well, it could explain some things that the standard model has trouble with, like the muon, which is kind of like a heavier electron, has this weird magnetic moment that doesn't quite fit the predictions.
A magnetic moment.
It's like a measure of how strongly a particle interacts with magnetic fields.
Okay, and the muons is acting out.
Right, it's a bit off. And a Z's prime boson that loves leptons could be the missing piece of the puzzle.
So it's like finding the Rosetta Stone for the subatomic world.
I like that analogy.
But before we get too lost in the subatomic world, what about the Z's prime boson's mass? How do scientists even begin to look for something when they don't know how heavy it is?
Right. That's key because the mass of a particle determines how much energy we need to smash other particles together to create it.
So bigger particle, bigger smasher.
Pretty much. And that's why places like the Large Hadron Collider, or LHC, are so important. They can create these incredibly high-energy collisions that might, just might, produce a Z's prime boson.
So it's like smashing two cars together and hoping to find a new type of engine part in the wreckage.
It's a bit more complicated than that, but you get the idea. And there are two main ways we're looking for it: direct searches and indirect searches.
Okay, from our pre-dive prep, I remember direct searches are like trying to create the Z's prime boson directly, then sifting through the data to find its decay products.
Right. It's like trying to find a needle in a haystack.
Yeah, sounds super tricky.
It is. There's a ton of background noise from other processes happening in these collisions, but physicists are clever folks. They come up with ways to filter out that noise.
And indirect searches. That's where you look for the Z's prime's subtle effects on other particles, right?
Exactly, like trying to see a planet by observing the wobble of its star.
I get it. So we could see the Z's prime's fingerprints even if we don't see it directly.
You got it. And in both cases, physicists focus on specific decay channels. Some particles are easier to spot than others, so we look for those.
So it's a bit like a detective following specific clues to find their suspect.
Exactly. And speaking of suspects, there are a bunch of different theoretical models that predict the existence of Z's prime bosons.
Oh, right. Each with its own unique characteristics and quirks.
Exactly.
Okay, so we've got our target, the Z's prime boson. We've got our methods, direct and indirect searches, and we've got our suspects, all these different theoretical models.
Now it's time to dig into those models and see which ones hold up best under scrutiny.
Right, because each model predicts different properties for the Z's prime boson, which would affect how we look for it.
Exactly. And that's what we'll be exploring in the next part of our deep dive.
All right, listeners, we've laid the groundwork for our Z's prime boson hunt. We've got the who, the how, and the why. But the real fun starts when we dive into the theories themselves.
Welcome back to the Z's Prime Deep Dive.
All right, so we've got the basics down, but now things are going to get a little more theoretical.
That's right, we're going to delve into the models that predict these Z's prime bosons.
And why is that so important?
Because these models aren't just abstract ideas, they actually guide physicists in their experiments.
Okay, so it's like having a suspect's profile before you start a manhunt.
Exactly. And in the case of the Z's prime, we have a whole lineup of suspects, each with its own unique set of characteristics.
From our pre-dive reading, I saw some models seem to be more popular than others.
Oh, absolutely. Some are definitely the greatest hits of Z's prime theories.
Like, what are some of those top contenders?
Well, one classic example is the sequential standard model Z prime.
I remember seeing that one. It's kind of like a copycat Z boson, right?
Yeah, in a way, it basically assumes that the Z's prime interacts with matter in a similar way to the regular Z boson, but with a higher mass.
So same interactions, just heavier and therefore harder to find.
Precisely. It's not the most groundbreaking model, theoretically speaking, but it's a useful benchmark.
Okay, so it's like the default suspect in our lineup.
Exactly. Now, moving on to some more exotic territory, we have models based on T3R and BL symmetries.
Those sound pretty intense.
Yeah, they get into some pretty fundamental properties of particles, like their charge and even their handedness.
Handedness, what, like left-handed or right-handed particles?
You got it. It has to do with their spin, and some particles only exist in one form, while others can be both.
Wow, that's wild. So what do these symmetries have to do with Z's prime bosons?
Well, these models predict Z's prime bosons with very specific interactions based on these underlying symmetries.
So it's like the symmetries are dictating the rules of the game.
Exactly. And different rules mean different experimental signatures, which helps us differentiate between models if we ever do find a Z's prime boson.
So it's like each model gives the Z's prime a unique fingerprint.
Precisely. Now, another set of models that I find really fascinating are the E6 models.
Those sound like they came straight out of science fiction.
They're ambitious, that's for sure. They predict a whole bunch of new particles, including, get this, multiple Z's prime bosons.
Hold on, multiple. We're not just talking about one, but a whole family of these things.
And it gets even crazier. They also predict exotic fermions. Those are particles that don't fit neatly into our usual categories of quarks and leptons.
Exotic fermions. It's like discovering a whole new branch of the particle family tree.
That's one way to put it. And that's just scratching the surface. We have models inspired by supersymmetry, theories with extra dimensions, composite Higgs bosons, you name it.
Wow, that's a lot of possibilities. But with so many models, how do physicists even know where to begin their search?
That's where the collaboration between theory and experiment comes in. The theories provide a roadmap, and the experimental results, in turn, help refine those theories.
Right, it's a two-way street.
Exactly. So let's shift gears now and focus on the experimental side of things.
Okay, let's see how these theoretical predictions are put to the test in the real world.
Well, one of the main players in this game is the Large Hadron Collider, or LHC. It's the world's most powerful particle accelerator.
Yeah, that massive underground ring spanning France and Switzerland. It's mind-blowing.
It really is a marvel of engineering. And by smashing protons together at nearly the speed of light, we create a shower of particles that we can study.
So we're recreating the conditions of the early universe just to see what pops out.
In a way, yeah. But finding those new particles is like looking for a needle in a haystack.
And from what I remember, something called resonances plays a key role here.
Absolutely. Resonances are one of the main things physicists look for in these collisions.
Okay, but back up a sec. What exactly is a resonance?
Think of it like pushing a child on a swing. If you push at just the right time, you add energy to the swing and it goes higher and higher.
Yeah, that makes sense.
Well, in particle physics, it's similar. When we collide particles at a specific energy that corresponds to the mass of a new particle, we see a peak in the data.
So it's like the collision rings at the frequency of the new particle.
You got it. That peak is what we call a resonance. And if we see a resonance at an energy that matches the predicted mass of a Z's prime boson, that's a pretty big deal.
So it's like tuning into a specific radio frequency and finally hearing a clear signal.
Perfect analogy. And these searches can be incredibly targeted. Physicists can look for resonances in specific decay channels, like pairs of leptons, pairs of quarks, or even a Z boson and a Higgs boson together.
Wow, a Z boson and a Higgs boson, that would be huge.
It would be a pretty strong hint that there's a connection between the Z's prime and the mechanism that gives particles mass.
Okay, my head is spinning a little bit.
It's a lot to take in, for sure.
But the big question is, with all this effort, have we actually seen any hints of a Z's prime boson yet.
Ah, the million-dollar question. And the answer is tantalizing, but not conclusive.
Of course it is. Science is rarely straightforward.
True enough. There have been some interesting anomalies in a few experiments, but nothing that definitively screams Z's prime.
So like seeing something out of the corner of your eye, but you can't get a clear view.
Exactly. For instance, a few years back, there was a buzz around an excess of events observed at the LHC. The energy suggested it could be a new particle around 750 GeV.
That sounds promising. Did they find it?
Sadly, no. As more data came in, the excess faded away. Just a statistical fluke.
Bummer.
It happens. But it highlights how these searches can generate a lot of excitement and really push the boundaries of our understanding.
So no confirmed Z's prime sightings yet, but the hunt goes on.
Absolutely. There are tons of experiments underway, and with every new run, we're getting more sensitive and exploring higher energy ranges.
It's like casting a wider and wider net, hoping to snag that elusive particle.
Exactly. And in the meantime, theorists are refining their models, making more precise predictions, and developing new analysis techniques. It's a constant back and forth driving the field forward.
So this is a story that's far from over.
Far from it. And that brings us to the big what if. What if we actually find a Z's prime boson? What would it mean for our understanding of the universe?
That's the really exciting part, right? We've talked about how to find it, but what about the implications of actually discovering it?
That's what we'll be diving into in the final part of our deep dive.
All right, listeners. We've explored the theoretical landscape of Z's prime models and gotten a taste of the experimental challenges and excitement. But the best is yet to come. Welcome back, everyone, for the final part of our Z's prime deep dive. We've talked about the theory, the experiments, the challenges, but now the big question. What if we actually find this thing? What happens then? What does it mean for our understanding of the universe?
That's the question that keeps physicists up at night. It wouldn't just be adding a new particle to the list. It would be like discovering a whole new continent on the map of physics.
Okay, I like that image. A whole new continent to explore, with all sorts of strange new landscapes and creatures we can't even imagine. What kind of wildlife might we encounter in this Z's prime landscape?
Well, one of the biggest mysteries it could help solve is dark matter. We know it's out there, we know it makes up a huge chunk of the universe, but we have no clue what it is.
Right, it's like this invisible force holding galaxies together, and we're totally in the dark about it.
Exactly. And some Z's prime models predict interactions with dark matter particles, like they might be speaking the same language.
So finding a Z's prime could be the key to finally cracking the code of dark matter.
It's one of the most exciting possibilities, and it doesn't stop there. The Z's prime could also help us tackle the hierarchy problem.
Remind me about that one again. Something to do with gravity being so weak compared to the other forces.
Right. It's like asking why a feather falls so much slower than a bowling ball, even though they both experience the same gravity. Some theories suggest extra dimensions could be at play.
Like, our universe is a multi-layered cake, and gravity is somehow leaking into these hidden layers.
That's a simplified way to think about it, but yeah. And here's the thing. Some Z's prime bosons are predicted to interact with these extra dimensions in unique ways.
So finding the right kind of Z's prime would basically confirm the existence of extra dimensions. That our universe is even more complex than we thought.
It would be a huge paradigm shift, but maybe the most profound implication of all is related to grand unification.
You mentioned that before, the idea that at super high energies, all the fundamental forces become one.
Exactly. And guess what's a key player in those theories? Z's prime bosons. They could be the missing link connecting all the forces.
So finding a Z's prime with the right properties could be like finding the master key to the universe.
That's the holy grail. But even if we don't find one anytime soon, the search itself is incredibly valuable.
Right, we talked about that. Every experiment, every analysis teaches us something, even if it's not a discovery.
It's like exploring a vast unknown territory. Even if you don't find what you're looking for, you're still mapping the land, making new discoveries.
So what's on the horizon for the Z's prime hunt? What are the most exciting things to look forward to?
Well, the LHC is getting a major upgrade, boosting its power. This will let us collect way more data, making it more likely to spot rare events like Z's prime production.
So we're sharpening our tools for the next stage of the search.
Exactly. And there are even proposals for future colliders that could reach even higher energies, opening up whole new possibilities.
It's pretty amazing to see how far we've come and where we're headed. This is a story that's definitely not over yet.
Not by a long shot. And while the experimentalists are busy smashing particles, theorists are refining their models, exploring new ideas. It's a constant dance between theory and experiment.
And who knows, maybe in the next few years, we'll be talking about Z's prime bosons, not as hypothetical particles, but as real, confirmed members of the universe.
It's a thrilling prospect.
Well, that wraps up our deep dive into the world of Z's prime bosons. Hopefully, we've sparked your curiosity and give you a glimpse into the incredible work being done to understand the universe at its most fundamental level. Thanks for joining us, and we'll catch you next time for another deep dive into the world of science and discovery.